Swayam Prabha. Digital India. Educated India.
Welcome to the third lesson of the sixth module, which is on stresses in beams part 3. In fact, in the last two lessons on this particular module, we have discussed aspects of the bending stresses in beams. Now, in this particular lesson, we are going to look into some more aspects of the stresses, and in fact, we will be looking into the effect of the shearing stress in beams. So, it is expected that once this particular lesson is completed, one should be able to understand the concept of shear stress in beams of rectangular cross section. One should be able to derive the shear formula, the formula for evaluating the shearing stress in a beam subjected to loads, and one should be in a position to evaluate shear stress in beams of rectangular cross sections for different loadings. Hence, the scope of this particular lesson includes, we will recapitulate the previous lesson, we will look into some aspects of the lessons which we have discussed in the last one. Concept of shear stress in beams of rectangular cross section, derivation of equation for shear stress in beams, and examples for evaluation of shear stresses in beams. We will be looking into some examples through which we know how to compute the value of the shearing stresses in a beam which is subjected to load. Now, let us look into the questions which were posed last time. Now, what is the impact of bending stress in arriving at a size of a beam? Now, if you remember, last time we had discussed in the last lesson that the flexural formula or the bending formula is given by this particular expression, that sigma is equals to minus my by I, which is written over here. Now, as you know, m is the bending moment, y is the point at which we are trying to evaluate the stress and the distance from the neutral axis, I is the moment of inertia. Now, when we are talking about the symmetrical section, as you know that neutral axis will be lying at the will be dividing the section in two halves, and the stresses at the compression or at the tension because of the positive bending moment will be of the same magnitude, and hence forgetting about the sign, we have written as absolute value of the maximum bending moment times y by I. Now, from this particular expression, if you look into sigma is the stress which is allowed in this particular member, or the it's a material characteristics. That means that if we know the allowable stress of that particular material, then we know how much stress limit of that particular section. Now, m max, the maximum bending moment, can be evaluated from the external loading that is acting on the beam member, and we have seen how to calculate the bending moment at different sections, and if we draw the bending moment diagram, then we can know at which location the maximum bending moment is occurring. So, we know m max, we know sigma. Now, these two parameters I and y, basically they are dependent on the cross sectional shape of the particular beam member. So, I by y, I is the moment of inertia and y is the distance of the point where we are evaluating the stress from the neutral axis, which is y. Now, this I by y is nothing but equals to m max by sigma. Now, m max we know from the loading, sigma we know from the material allowable stress. So, we can get the value of I by y, and from this particular numerical value of I by y, we can select a particular section, and this particular parameter I by y generally we designate by z. So, if we can select a member of this Z value, then if we go for a section which is which has higher Z value than Z required, then the section will be able to withstand the bending moment that is occurring because of the load. So, that means if we select a member which has the I by Y value is larger than we are getting from this expression m by sigma, then the member will be in a position to withstand this particular load. But if we provide a section for which the Z value is less than I by Y, then naturally the stress level will go beyond the capability of that particular material, and the member will fail. Now, if the member is unsymmetrical with respect to x axis, as we had discussed last time, supposing if we have a cross section which is something like this, which is symmetrical with respect to y axis, but unsymmetrical with respect to x axis, then these y values will be different from the neutral axis for two ends, and these we can designate as y1 and y2, and correspondingly we will have two values of I by y. We can call one as z1, which is equals to I by y1, other one will be z2, which is I by y2. Now, smaller the value of y1 or y2 as having the same I, we will have the larger value of z, and we will have to see corresponding to the higher value of z, if we choose a particular section, then that particular section will be able to withstand the stress. So, we will have to decide whether it is a symmetrical section or unsymmetrical section with respect to x axis. Accordingly, we will have to find out the value of I by y, and correspondingly we will have to select a particular section which satisfy this particular requirement. So, this bending stress has great impact in selecting a particular sectional configuration of a member, where we will have to find out the size. Now, the next question is, what is the relation between curvature and the bending stress in a beam? Now, this is a very straightforward question, and I think you know the answer of it. This is we have seen the bending equation, which is m by I is equals to u by rho equals to sigma by y, where m is the bending moment, I is the moment of inertia, E is the modulus of elasticity, rho is the radius of the axis of the beam, sigma is the bending stress, and y is the distance of the point where we are evaluating the stress from the neutral axis, and sigma, mind that, is a normal stress which is getting generated because of the bending in the particular section. So, now if we relate the stress with the curvature, that means if we take this particular relationship, E by rho is equals to minus sigma by y, then we get this, that sigma is equals to minus E y by rho, and y by rho, as you know that we have termed this as kappa, this is curvature. So, this is how the stress is related to the curvature through this parameter E and y, and this we can evaluate at a particular point with respect to the neutral axis. Now, the third question was the what is meant by section modulus. Now, in the course of discussion over here, we have defined the term. In fact, we have said that z is a parameter which is I by y. In fact, this is what we call as section modulus. The ratio of moment of inertia of the section to the extreme fiber distance from neutral axis of the section is known as the section modulus. So, if I is the moment of inertia and y, let us call this as y max, which is the extreme distance from the neutral axis of the outer fiber, then I by y max is equals to the z, the section modulus of a particular section, which we decide from the bending moment and the stress. Well, then having known this, as we have seen in the previous two lessons, that we have computed the values of the bending stress. That means, a beam member, when they are subjected to a stress resultant which is a bending moment, for that we could evaluate what is the value of the normal stress because of such bending. Now, as you have noticed that a beam member, when they are subjected to loads, not only they are subjected to the bending moment, but at locations they are subjected to the shear forces also. Now, places for some loading where it is exclusively bending moment, then corresponding stresses which we get are the bending stresses. But in some zones where the bending is associated with shear force as well, there we got to compute the value of the normal stress through the bending equation as we have done, as well as we need to evaluate the value of the shearing stress as well. Now, in this particular lesson we are going to look into how to compute the value of the shearing stress at a particular location where we know the value of the shearing force for the external loading that the member is subjected to. Now, let us look into this particular figure wherein we have taken a part of the beam segment which is subjected to the loading. Now, this is the shear force, positive shear force acting on this particular face, and this member is of rectangular cross section having a depth h and width b. Now, we assume two aspects over here. One is that shear stresses act on a cross section and are parallel to the shear force. That means, at a particular section where we have the shearing force, we assume that the shear stress is parallel with the shear force in that particular cross section. It is also assumed that the shear stresses are uniformly distributed across the width of the beam. It is reasonable to assume that across the width of the beam the shear stress is uniform. However, there could be variation of the shear stress along the depth of the beam, but at a particular point along the width we assume that the shear stress is uniform. So, we assume two aspects. One is the shear stress, direction of shear stress we assume is in line with the shearing force which is acting at a particular cross section, and the distribution of the shear stress along the width is uniform. Now, if we do that, then say for example, if we take out a small segment from this particular beam, then we get the segment something like this. This is the segmental size which is here. Now, along the width the shear stress is uniform as we have assumed at the moment, and so in the horizontal direction we will have the complementaries here, as we have noticed earlier that if we take a section, if we have a vertical shear, then we have a horizontal shear as well, which we call as a complementary shear. Now, if we look into this particular elements, the small element which we have exaggerated, now this is the shearing stress, positive shear stress which we have on the vertical face. Consequently, we have the horizontal shearing stress which is the complementary shear stress. Now, please note one point over here, that if we take this particular element say closer to the top surface, now on this particular surface, on the top surface there is no other element, hence the shearing stress on the top surface is 0. So, at the top point, since the horizontal shear stress is 0, so the vertical shear stress at the extreme ends also are 0. So, at the top and at the bottom the shearing stress is also equals to 0, at plus minus h by 2 the shearing stress is 0. Now, let us evaluate that what is the magnitude of the shearing stress in terms of the sectional parameters. Now, before we really go into the evaluation of the shearing stress, you can think of a small experiment, a simple experiment, that we take a number of small beams which are supported on supports, and these beams individually they are resting one after another, and we apply a load onto top of this particular beam. It is expected that it is undergoing a deformation in this particular form as it is shown over here, and since they are not connected with each other, now the bottom part of this particular top beam will be undergoing a extension or the tension, the top fiber of this particular beam will be under compression. So, there is expected to be some amount of slippage, and since if we say that the frictional resistance is small, then there will be a substantial change in the length between these two surfaces. Now, this indicates that if supposing if we could hold all these three segments together by some means, by application of a glue or by nailing, then the whole system would have acted as one unit. Now, this indicates that some amount of stresses are acting at the interface between these elements, and this is what is the horizontal shear stress, which retains these three segments together if they are tied together, and they can resist the load in terms of the stresses. Now, let us look into how do we compute the value of the shearing stress in a beam. Now, we consider a segment of the beam which is loaded, and let us say these are the two sections at a distance of dx. Let us call this section as AA and this as BB, and on face AA we have this shear force V and the bending moment M. On the right face we have shear force V plus dV and moment as M plus dm. We expect that from AA to BB over dx distance as we move, there is a change in the shear force and the bending moment. Now if we separate out this particular element and look into the stresses in that, now this is the stress distribution which is shown. This is corresponding to the bending stress. They are the normal stress that is acting in the beam, and here we have considered the moment part only, M and M plus dm. There will be stresses because of the shearing action as well, but since we are interested at this moment to compute the value of the horizontal shear stress, let us keep the vertical shear stress apart. So we are looking into only the stress because of the bending moment only. Now if we consider a small segment of this particular beam which is at a distance of, let us say, y1 from this particular neutral axis, then if we separate out this particular segment and look into the stresses, the stress distribution will be something like this, that here we have the normal stress which is getting generated because of the bending moment M plus dm. On this side you have the normal stresses which is getting generated because of the bending moment M, and at this particular section or the cross section of this particular member, we will have a horizontal shear which is acting at this face. Now there are vertical shear on these faces which we are not accounting at the moment. Now the cross section of the beam at this particular section, section AA, is like this, where the width is B and depth is h, and the distance from the neutral axis is h by 2, and we are considering a section which is at a distance of y1 from the neutral axis. So this is the section which we are looking into, and so is the section at BB is a rectangular one having width B and depth h, the same configuration, and we are considering this particular segment. Now if we consider a small area dA, then the force which will be acting is equals to sigma times dA, and this sigma we can compute from the expression as we have learned in terms of the bending. Since we are considering only the bending moment acting in this particular section, so the stress sigma due to bending is equals to my by I, which we have looked into the flexural equation. So on this side, this particular force F1 will be the stress multiplied by the area of this particular segment, and on this side the force F2 will be the stress which is generated because of M plus dm multiplied by this segmental area, which will give us F2. So in this particular element we have force F1, we have force F2, and we have force F3. So if we take the equilibrium of these forces in the horizontal direction, we have F1 minus F2 minus F3 there equals to 0. Now let us look into that, how do we calculate these F1, F2 and F3. Now here you note that the force F1 is getting generated because of the bending moment M. So My by I multiplied by the elemental area dA, and the segment is from y1 up to h by 2. So this gives us the value of F1. Likewise the value of F2 is equals to integral minus of M plus dm times y by I multiplied by dA, and again it is integrated from y1 to h by 2. So this gives us the value of F2. Now if we write down the equilibrium equation, which is F1 minus F2 minus F3 equals to 0, and thereby it gives us F3 is equals to F1 minus F2, and F3 is the force which we are trying to find out. So if we substitute for F1 and F2, this is F1 is minus integral y1 to h by 2 M y by I times dA minus and minus minus plus integral y1 to h by 2 m plus dm y by I dA, and this is equals to F3. Now, if we this my by I gets cancelled, so we are left with dm by I y1 to h by 2 integral y dA, and this particular parameter integral y dA we designate as q, q as equals to integral y dA, and in this particular case it is from y1 to h by 2, and F3, as you can observe from the previous one, that F3 is acting at the section of this particular beam segment, wherein the width of the beam is equals to b and the length we have considered as dx. So, we have taken a dx segment from the beam of width b. So, the area over which the shear is uniformly distributed is equals to b times dx. So, if tau is the shearing stress, then the force that is acting at that particular cross section is tau times b times dx, stress multiplied by the area. So, F3, that is why it is written as tau times b dx, and hence if we equate these two, we get a relationship between the shearing stress and the moment. Tau b dx is F3, this is equals to dm by I integral y1 to h by 2 y dA, which we are designating as q. So, tau basically is equals to then dm by dx times I by b times q. Now, you can recognize this particular parameter dm dx. Dm dx is nothing but equals to v, is the shear force, the rate of change of the bending moment along the length is equals to the shear force. So, what we can, sorry, this is I times b. So, tau from this particular expression is equals to v times q divided by I into b. So, this is the expression for the horizontal shear stress. Tau is equals to the vertical shear force v, q is the area, is the moment of the area which is above the section where we are trying to calculate the shearing stress. We are trying to calculate the shearing stress in the section which is at a distance of y1 from the neutral axis, and the area above y1 from y1 to h by 2 is the segmental area. The moment of that particular area with respect to the neutral axis will give us the value of q. So, we know the vertical shear force v, we can compute value of q, we can find out I is the moment of inertia of the section with respect to the neutral axis, b is the width. So, we can compute the value of the shearing stress, and as you can observe from this particular expression that at a particular cross section v, I and b, these three parameters are constant or the same. Only parameter which is varying is q, because q is dependent on y, is the distance from the neutral axis, hence along the depth of the beam the shear stress will be varying. Shear stress is dependent on q and q in turn is dependent on the distance y. So, we can compute the value of the horizontal shear stress at a particular section. Now, as we have seen that the horizontal shear stress is the complementary to the vertical shear stress. So, the vertical shear stress also will have equal in magnitude of that horizontal shear stress. So, once we compute this expression, so b q by I b, so that is same as that for the vertical shear stress as well. So, from this particular shear formula which we have just derived, we find that the shearing stress, expression for shearing stress tau is equals to v q by I b, and this can be used to evaluate shear stress at any point in the cross section of a rectangular beam. Now, rectangular beam means a beam having a rectangular cross section. Now, the term q is the first moment of the cross sectional area above the level at which we are looking for the shear stress, and for a particular section the shear stress varies with the parameter q, because v, I and b being these parameters being constant for a particular section, the only parameter which is varying is q, and q is varying with respect to y1. hence the shear stress also along the depth it varies, and we get the distribution of the shear stress on the depth. Now, let us look into that how the shear stress varies across the depth. Now, we have obtained the value of the tau shearing stress as equals to V q by I b. Now, q for this particular beam, as we have seen, is integral y dA. Now, supposing in this particular rectangular section where the width is b and height is h for this beam, the neutral axis divides the section in two halves. Now, we like to find out the shear stress across this particular section, which is at a distance of y1 from the neutral axis. Hence, this is the segment which is under consideration, which is above the point above which we are computing the shearing stress. So, if we compute the value of q for this particular section, so q is equals to integral. Now, for dA, if we take a small strip over here having width dy, so dA is equals to b times dy and y varies from y1 to h by 2. So, this is equals to b by 2 times y square, y dy is y square by 2 and y square is h square by 4 minus y1 square. So, this is the value of q. So, tau is equals to v by I b, b by 2 times h square by 4 minus y1 square. So, b gets cancelled. So, this is equals to v by 2I times h square by 4 minus y1 square. Now, please note that the shearing stress tau varies parabolically across the depth, it varies with y1 square. Now, when y1 is equals to 0, we get the maximum value of tau. So, that implies that at the neutral axis we get the maximum value of the shearing stress, and as y1 becomes h by 2 plus h by 2 or minus h by 2, the value of the shearing stress becomes 0, and as we have noticed earlier that at the top and the bottom of the beam the value of the shearing stress is 0. So, if we plot the shear stress distribution, it looks like this, that at the top and the bottom the shear stress is 0 and over the depth it is varying parabolically, and at the neutral axis we have the maximum value of shearing stress. And what is the magnitude of this maximum value? If we call this as tau max, tau max is equals to b by twice I into h square by 4. Now, if we write down that tau is equals to b h square by 8I. Now, I for this particular rectangular section is equals to b h cube by 12. Now, if we substitute that, this is equals to v h square divided by 8 b h cube times 12. So, h square gets cancelled h. So, 4 3, this is 2. So, this is equals to 3 by 2 v divided by, now b times h is nothing but the cross sectional area. So, we write this as a. So, tau max, the maximum value of the shearing stress in a rectangular beam is equals to, we call this as tau max, corresponding to the maximum shear force V max, and 3 by 2 V max by A will give us the value of the tau max. And as you can see that across the depth the shear stress varies for a rectangular beam in a parabolic manner, and at the neutral axis we get the maximum shear stress, and at the extreme ends the shearing stress is 0, and the value, the magnitude of the maximum shear stress is equals to 3 by 2 V max by A. Now, as we had assumed in the beginning, if you remember, that the shear stress, though it is varying across the depth, along the width we assume that the shearing stress is constant. So, that means at this particular point, this is the value of the shearing stress, along the width this particular value is constant. So, as we had assumed in the beginning, two aspects. One is the shear stress acts along the direction of the shearing force, and the shearing stress at a particular point is uniformly distributed across the width. Now, here one aspect is to be remembered is that we really do not bother about the sign of the stress as such. We consider that the direction of the shear stress is along the direction of the shear force. So, from the bending moment and shear force diagram, from the shear force diagram, we know the direction of the positive or negative shear, and accordingly we take the direction of the shearing stress as well. Now, with this background, now let us look into then what are the steps that we need for evaluating the shearing stress at a particular point. Now, to evaluate the shear stress at a point in a beam, first of all we need to find out the vertical shear force V in the cross section, where we are trying to find out the particular shear stress. That means, at a particular point where we are evaluating the shear stress, we will have to find out that that particular point is in which section, and at that particular section we will have to calculate the value of the shear force, and this we can carry out by drawing the shear force diagram. Once we draw the shear force diagram in the length of the beam, at different point we know the values of the shearing force, and the point where we are interested to evaluate the shearing stress, we like to find out at that particular point where, or the particular section where that particular point lies, what is the magnitude of the shearing force. That is the first thing. Secondly, in the cross section we will have to locate the neutral axis, and we will have to compute the moment of inertia about this neutral axis. Then, as you have seen, that we will have to compute the value of Q, which is the first moment of the area of the section above or below the point of where we are trying to find out the shear stress. As we have seen in case of a rectangular beam, supposing if we take a section where we like to find out the shear stress, we concentrate on the area where we are trying to find out the shear stress, either above or below of that particular segment, and we take the moment of that area with respect to the neutral axis, and that gives us the value of Q. So, once we know Q, so this gives us I, B is known, and B is the width of the beam. So, that gives us the shear stress from this particular expression, which is BQ by IB, and we can find out the value of the shear stress at that particular point. Well, then with this background, let us look into some of the examples on how to evaluate the shear stress and the bending stress at a particular point in a beam having different cross sections. Now, this is the example which I had given to you last time, that the cross section of the beam is like this. Here is like an inverted U. This particular section is symmetrical with respect to y axis, but it is unsymmetrical with respect to the horizontal axis. Hence, first thing is we will have to compute or locate the position of the centroid of this particular section, so that we can find out the position of the neutral axis and consequently the value of the moment of inertia I. Now, fortunately in this particular problem, these values are given, the location of the neutral axis is indicated or the location of the centroid is known, which is 84 millimeter from the top of the cross section, and the moment of inertia about the neutral axis is given as 75 into 10 to the power 6 millimeter to the power 4. Now, what we will have to do is, here this particular beam is subjected to a concentrated load at this overhang part, and over this length there is a load of capital W per meter length. We need to evaluate the value of W, so that the bending stresses are 60 megapascal in tension and 100 megapascal in compression. Now, we will have to find out the maximum value of load that we can apply in the beam, so that the tensile stress do not go beyond 60 megapascal and the bending compressive stress does not go beyond 100 megapascal. Now, if we have to satisfy these two criteria, then what is the value of W that we can apply on this beam, and that is what is to be determined. Now, to do that, let us find out first the where the maximum bending moment and the maximum shear force occurs. Of course, here we are dealing with only the bending stress. So, if we can know where the maximum bending moment is, we can compute the bending stresses. Now, as usual, this particular beam is supported on a hinge over here and roller on this particular end. So, we will have a reactive force, vertical reactive force RB, and a horizontal reactive force HB, and here a vertical reactive force RC. Now, since we do not have any horizontal force, so HB equals to 0, so we will be left with RB and RC, and the values of RB and RC, if you compute from these, RB plus RC is equals to W plus 4 times W, so 5 W, and if you take the moment of the forces with respect to B, we can get the value of RC and consequently the B. Now, if you compute the values of RB and RC, you will find that the values of RB and RC will be like this. RB is equals to 3.5 W and RC is equals to 1.5 W. Now, here if we like to plot the shear force diagram, and if we take a cross section over here and take the free body of the left part, then we have the shear force and the bending moment, and here we have the load W. Now, since at this particular segment we do not have any other load, so V is equals to W. So, we have a positive shear from A to B, and that is what is indicated over here, and the magnitude of that positive shear is equals to W. V is equals to plus W over here. Now, if we take a free body diagram of this beam and cut the beam at this particular section and take the free body of this left part, then the free body diagram will look like this. This is reactive force RB, here we have the load W, and here we have the shear force B and the bending moment M, and the load is distributed over this particular segment, and let us call that this particular distance is X. So, V plus RB minus W into X is equals to 0. So, V is equals to minus RB plus W into X. Now, RB is equals to 3.5 W. Now, so shear force at this particular end beyond B, if we try to find out that at any segment, let us say at a distance C, when X is equals to 4 meter, so this is 4 W plus W 5 W, and RB is 3.5 W. So, V is equals to plus 1.5 W. So, this is the shear force at the end C, and at point B, if we take W, X is equals to 0. So, RB is equals to minus 3.5 and W is W. So, this is equals to minus 2.5 W. So, at point B it is minus 2.5 W, at point C it is 1.5 W. Now, since it is changing from minus to plus, so somewhere along the length the shear force is equals to 0. Now, if we set the expression for shear as equals to 0 from this, that V is equals to minus RB plus WX, V is equals to 0 means it gives that RB is minus 3.5 W. So, minus 3.5 W plus W is minus 2.5 W. So, that gives us that minus 2.5 W is equals to 2.5, so W times X is equals to 2.5 W. So, W gets cancelled. So, X is equals to 2.5. So, it indicates that at a distance of X equals to 2.5, the shear force is 0. So, it changes sign from negative to the positive, and here the value is 1.5 W. And as we know that where the shear force is 0, at the corresponding point we will get a value which is a maximum in the bending moment. Now, if we compute the value of the bending moment for different segments, if we take the moment from this particular free body diagram, now at this particular free body you see M is equals to W times X. So, when X is equals to 2, M is equals to, now M and W they are in the same direction, so M is equals to minus W times X. Now, when X is equals to 2 meters, M is equals to minus twice W. So, this is what is indicated over here. The magnitude of this moment is twice W. Now, at this particular point again we have seen that the shear force is 0. Now, here we are getting the change in the shear from positive to the negative sign. So, here we expect some higher value of the bending moment, or as we have seen that the maximum bending moment occurs either where the shear force is 0 or the point where shear force changes its signs from the negative to the positive. or the vice versa. Now, at this particular point, if we compute the magnitude of the bending moment, now the expression for the bending moment for this particular free body diagram, if we look into, is equals to that m plus w is acting in the same direction. So, w times x plus 2 minus rb into x plus w into x square by 2, this is equals to 0. So, the bending moment m is equals to rb into x minus w x square by 2 minus w into x plus 2. Now, if we substitute the value of x as equals to 2.5, where the shear force is 0, we get the magnitude of m as 1.125 w, and this is the maximum positive bending moment that occurs in this particular beam. So, you see we have two maximum values of the bending moment, one is the positive maximum, another is the negative maximum. So, the maximum positive bending moment is equals to 1.125 w and the maximum negative bending moment is equals to twice w. So, along the length of the beam, as we see, once we plot this bending moment diagram, it is clear that at two locations we get the maximum value, one is the maximum positive bending moment and at the other point we have the maximum negative moment. And we got to compute the value of the stresses in the beam corresponding to these two values of the positive and the negative bending moment, and then we will have to take a decision on what load, maximum load we can apply on this particular beam. Now, let us compute the value of the stresses corresponding to these two bending moment. So, we have obtained that the maximum positive bending moment is equals to 1.125 w kilonewton meter and maximum negative moment is equals to 2 w kilonewton meter. Now, as you have noted earlier, that supposing if we have the negative bending moment, our negative bending moment sign is like this, and this causes tension at the top and compression at the bottom. Now, if we calculate the bending stress sigma, which is equals to m y by I. Now, I of this particular section is given over here, which is 75 into 10 to the power 6 millimeter to the power 4. So, the stress which will be acting at the top for this negative moment is the tension, and tensile stress is 60 MPa, thereby for the first case we have 60 is equals to m is twice w, so much of kilonewton meter times 10 to the power 6, so much of Newton millimeter, multiplied by y, y is the neutral axis from the top distance, which is 84 millimeter, because maximum tensile stress will occur at the top fiber. This divided by I, which is 75 into 10 to the power 6, so much of megapascal. Now, from this if you compute the value of w, w comes as equals to 26.8 kilonewton. So, this is one value of the w which you get corresponding to the maximum tensile stress corresponding to the maximum negative bending moment. Now, what is the value of the compressive stress correspondingly? Now, allowable compressive stress is 100 MPa. So, 100 corresponding to this moment is equals to twice w into 10 to the power 6 into 116 is the bottom fiber extreme fiber distance from the neutral axis. So, this is 116 divided by I, which is 75 into 10 to the power 6. Now, from this if you compute the value of w, the w comes as equals to 32.33 MPa. So, corresponding to this value of the bending moment, which is twice w, the maximum negative bending moment, we get the tensile stress at the top and the compressive stress at the bottom, and corresponding to these limiting values of the tensile stress and the compressive stress, we get the two values of w's, which is 26.8 kilonewton and 32.33 kilonewton. Now, obviously, if we have this particular load applied on this beam, then the stress level in tension will be exceeding 60, and as a result the beam will fail. So, we will have to limit ourselves to this load value of 26.8 kilonewton meter. Now, before we take a decision on this particular loading, we will have to check up with respect to the stresses that develop with respect to this positive bending moment. Now, let us compute the value of the stresses that develops because of the positive bending moment, which is of magnitude 1.125 W. Now, if we calculate the value of the stress, now the positive bending moment, which is of this kind, will cause a compression at the top and tension at the bottom. So, if we compute the stress corresponding to the one positive bending moment, the compressive stress at the top is equals to 100. This is equals to 1.125 W into 10 to the power 6 so much of Newton millimeter, multiplied by the distance of the top fiber from the neutral axis, which is 84, divided by I, which is 75 into 10 to the power 6. Now, from this if we calculate W, the value of W comes as 79.4 MPa, I mean so much of kilonewton. Corresponding to this particular moment, if we compute the stress at the bottom, which is a tensile stress, which is 60, now 60 is equals to 1.125 W into 10 to the power 6 into the distance of the bottom fiber from the neutral axis, which is 116, divided by I, which is equals to 75 into 10 to the power 6. Now, from this if you compute the value of W, the value of W comes as 34.5 kilonewton. Now, out of these two values, we find that 34.5 kilonewton is the lower value, and because if we apply 79.4, naturally the stress level here will exceed and the member will fail. Now, out of the 4 values, now that if you look into, we have obtained 4 values. One is 26.8 kilonewton and 32.33 kilonewton in earlier case, corresponding to the maximum negative moment, and corresponding to the positive moment we have 79.4 kilonewton and 34.5 kilonewton. Now, out of these 4 values, we find that 26.8 is the lowest value, and this is the value which we will have to apply on the beam member, so that the all other stresses are within limit. Now, if we apply a load more than 26.8 kilonewton, as we have calculated for corresponding to the other cases, then the stress level in other values will exceed. Hence, we will have to apply the minimum possible W's which we have evaluated out of these 4 cases, and that is the maximum load that we can apply on the beam, so that the beam functions and safely carry the load what is indicated in the beam. Well, we have another example. In fact, this is the example which corresponds to the one which we have discussed today on the aspects of shear stress, that a simply supported beam is subjected to an uniformly distributed load of 10 kilonewton per meter, including its own weight. Now, determine the normal and shear stress at point C. Now, at this particular point, we will have to find out the value of the normal stress which is generated due to bending, and the value of the shear stress. Now, the point C is at a distance of 150 millimeter from the bottom fiber. That means that this is the position of the neutral axis, because it is symmetrical. So, point C is somewhere here along this length, which is 50 millimeter from this neutral axis. So, we will have to compute the normal stress and the shearing stress. Also, we will have to find out the value of the maximum normal and the maximum shear stress. Now, naturally, to compute the value of maximum normal and the maximum shear stress, we will have to know along the length of the beam at which point you have the maximum bending moment and the maximum shear force. And to ascertain the value of the maximum bending moment and the maximum shear force, you will have to draw the bending moment and shear force diagram, and then correspondingly you can find out where the maximum bending moment and the maximum shear stress is occurring. Now, as usual, we have this particular end is on hinge. So, you have the vertical and the horizontal reaction, which is RA and HA. Now, you have the vertical reactive force RB over here. So, as usual, you got to compute the value of RA and RB, and of course, the HA is equals to 0, because you do not have any horizontal force in this particular member. Now, this particular member is symmetrically loaded with symmetrical supports. As we have seen earlier, that when you have uniformly distributed load, the reactive values will be equal. Ra is equals to Rb, and that is equals to the uniformly distributed load 10 multiplied by the length of the beam by 2. So, this is equals to 15 kilonewton. So, the reactive values will be equals to 15 kilonewton. In fact, this we can evaluate as we have done earlier, that Ra plus Rb equals to 10 times 3, and if we take the moment of the forces with respect to one of the supports, you can get the value of one of the reactions. So, these are the reactive values. Ha is 0, Ra is 15 and Rb is 15. Now, let us look into the shear force and bending moment diagram of this particular beam along the length, so that we can compute the value of the stresses. Now, Ra we have obtained as 15, Rb also as 15. Now, if we take a free body diagram of this particular member on the left hand segment, we have the support reaction Ra, and on this we have the shear force V and the moment M. So, V plus Ra equals to 0. So, V is equals to minus Ra. So, we have the 15 kilonewton negative as the shear force over here. Now, since there are no other loads acting on this particular beam member, so V at well, we have V minus at this particular segment, which is at a distance of x, we have uniformly distributed load also. So, minus Ra plus the 10 kilonewton times x. So, at x equals to 0, the V is Ra, this is the shear force. Now, as we go along the length, the value of x changes, and consequently there is a change in the shear. Now, as you can see that when x is equals to half the length is 1.5, then shear force becomes 0. So, at the central point, the shear force crosses the baseline and goes to the other side, and it becomes a positive shear over here. If you take the value of x as 3 meters, then you get the value of V as equals to plus 15. So, from minus 15 to plus 15 it changes, and at the central point it becomes 0, which is because of the symmetrical loading. And this kind of distribution of the shear force, we had seen it earlier, that if you have a simply supported beam subjected to uniformly distributed load, then the half the total load is on one support, and gradually it varies, becomes 0 at the center and goes to the other end. Now, also if you compute the bending moment M, the value of the bending moment M is equals to Ra into x minus W x square by 2. Now, Ra is equals to 15. So, 15 times x minus W is 10. So, 5x square. Now, at the center where x equals to 1.5, if you compute, the value of the bending moment will be equals to 11.25 kilonewton meter. So, that is the maximum bending moment that we get corresponding to this 0 shear force. Now, what we got to evaluate in this particular problem is, we will have to find out the maximum bending stress and the maximum shearing stress. Now, from these particular diagrams, we can see that the maximum value of the bending moment is equals to 11.25 kilonewton meter, and the maximum value of the shear force which is acting at the support is equals to 15 kilonewton. And we got to compute the value of the bending stress and the shear stress at point C, and maximum value of the bending moment at point C is equals to 6.25 kilonewton meter, and the value of the shear stress at point C is equals to 10 kilonewton. So, corresponding to these values of the shear force and the bending moment, if we compute the stresses, then the stress and the moment becomes like this. Now, the value of bending moment or the bending stress, the normal stress, say at C, first let us calculate at C. At C, the bending stress is equals to My by I, and at C moment is 6.25 kilonewton meter. So, this is 6.25 into 10 to the power 6 into y is at a distance of 50 from the neutral axis, because this is 150 from the bottom. So, this is 50 divided by I is equals to 100 to 200 cube by 12, and this if we compute the value of the sigma, this comes as 4.7 MPa. Now, if we compute the value of the shearing stress at this particular point, now tau is equals to V q by I b. Now, V we know is 10 kilonewton at this particular section, q is equals to a y bar or integral y dy y dA. Now, this if you calculate, we will have to take the segment above the place where we are evaluating the shear stress. Now, this is the place where we are evaluating the shear stress. So, we got to compute this particular segment, and this particular segment area is equals to 100 times 50. So, q is equals to 100 times 50 is the area, and its own CG is 25 from the top. So, from the neutral axis it is 75. So, this multiplied by 75 is q, and I again is 100 into 200 cube by 12, and b is equals to 100. So, if you substitute this, you get the value of tau as equals to 0.5625 MPa. So, this is the value of the shearing stress that you get at point C. Now, corresponding to the maximum value of the bending moment and the maximum value of the shear force, if you compute the stresses, we get the values like this, that bending stress sigma again as m y by I, and m max is equals to 11.25 into 10 to the power 6, and y is the extreme point, which is the maximum value, is equals to 100, and correspondingly 100 times 200 cube by 12. So, this gives us the value of the bending stress, and if you compute, this comes as 16.875 MPa. Now, for a rectangular section, as you know, that the maximum shear stress tau max is equals to 3 by 2 V max by area. Now, V max here is 15 kilonewton. So, and area is equals to 100 multiplied by 200. So, if we substitute these values, the maximum shear stress comes as 1.125 MPa. So, at point C, we can compute the value of the bending stress and the normal stress, normal stress and the shearing stress, and the maximum value of the normal stress and the shearing stress from this particular diagram. Now, we have another problem wherein the beam which is shown over here, we will have to find out the stress at a point which is 30 millimeter above the bottom of the beam at section C. That means, we will have to compute the value of the shearing stress at this particular point and at this location, which is at a distance of 30 millimeter from the bottom. Now, here the cross section is symmetrical again with respect to the vertical axis. Now, here we have two rectangular components joined together, and neutral axis is located at a distance of 62.5 millimeter from the bottom fiber, and the moment of inertia is indicated over here. Now, here of course, we need not calculate the shear force of the bending moment diagram as such, but we can find out the shear force diagram, and from which we can compute the value of the shear stress. Now, at this particular location, as we can see that the value of the shear force is equals to 6.67 kilonewton, and correspondingly, if we calculate the value of the shear stress, which is equals to 6.67 times 10 to the power 3, this is V, times Q by I b. Now, b in this particular case, if you look into, is equals to 100. So, if we compute the value of the shear stress tau is equals to 6.67 into 10 to the power 3 multiplied by q, which is equals to 100, because this is the section which we are looking into. This is 100 times 30, and this is 62.5 minus 15, which is equals to 47.5 divided by I times b, which is 100. If you compute that, this comes as 0.5 MPa. Well, you have another problem. You look into this particular problem, that a beam which is subjected to two concentrated load, you got to compute the maximum value of b, so that the bending stress does not exceed 60 MPa and shearing stress does not exceed 10 MPa. So, we will look into this particular problem next time. Now, to summarize then, in this particular lesson, we have included the concept of the previous lesson. We have looked into the concept of shear stress in beams with rectangular cross sections. We have looked into the derivation of equation for shear stress in beams, and we have looked into some examples to evaluate shear stresses in beams. Now, the questions given for you are: what are the assumptions made in deriving the shear formula, what is the limitation of shear stress formula, and what is the value of shear stress in a cantilever beam subjected to a moment at its tip, and we will look into the answers of these questions in the next lesson. Thank you very much.